Let's look at one more example of finding a volume using this cross-sectional area idea. So let's find the volume that we get by rotating this region below about the line x equals 3. So we're looking at the region enclosed by y equals x, the x-axis here, and the line x equals 2, so this vertical line. So we're rotating this triangular region down here. When we rotate this around the line x equals 3, what we get is, so something that, right, it has this circular top, side is slanted like this, and then it has sort of a wide circular bottom. So it's like a cone, but it has this hole down the middle, right, that corresponds to this gap here. So if we sliced this vertically, we get some pretty funny shaped cross sections. But if we slice this horizontally, we get just washers, or big circles with circular holes cut out of the middle. So here's a typical cross section. So there's the inside circular hole, and then here's the big outside circle. So we know that we can just integrate the area of the big circle minus the area of the small circle. So that's pi times the outside radius squared minus the inside radius squared. It looks like we have one cross section for every y value, right? Here's the cross section at the bottom is at y equals 0. The cross section in the middle is somewhere in the middle. The cross section at the top, well, we'll have to figure out where that is, but since it's x equals 2 down here and this is y equals x, this top cross section is at 2. So it looks like we're integrating with respect to y, and our bounds must be from y equals 0 to 2. So all we need to do is figure out what are the inside and outside radius functions. To work that out, let's actually draw what the outside radius is. We'll do the inside radius in just a second. So on this cross section in the middle, the outside radius spans from this blue dot on the left over to the axis of rotation. Now this is quite different than earlier examples where we always rotated about one of the coordinate axes. Here we're rotating around a vertical line, but it's not the y-axis. So what we need to do is write this distance, right? This is the outside radius. We need to write this distance as a function of y. To do that, well, this distance that is the outside radius is a horizontal distance. And to find a horizontal distance, all you need to do is subtract the x coordinates of these 2 points. And to make this radius positive, we should do big minus small. So we'll do the big x coordinate, which is 3, minus the smaller x coordinate, which is x. But remember, our plan was to write everything in terms of y. So this x here in our expression for the outside radius, we need to translate that into y's somehow. But this x came from this point on the left, and it's on the line y equals x. So on this line, y and x are the same, so we can actually just replace this x with y, because they're equal on this line. So the outside radius function is just 3 minus y. Now we can do the same thing for the inside radius function. Right? The inside radius is the distance from the axis of rotation over to the inside circle. And just like before, in principle, this is a function of y, although in this particular example, it's a constant function. But again, because this is a horizontal distance, we can just subtract the x coordinates that give us these 2 positions. So the bigger x coordinate is 3, and the smaller x coordinate is 2, and so the difference is 1. So the outside radius is 3 minus y, the inside radius is 1, so we can put that into our integral here. So integral from 0 to 2 of pi times outside radius is 3 minus y squared minus inside radius is 1 squared dy. All right, so we'll evaluate this integral in just a moment, But what I want to point out here is that because we are not rotating around a coordinate axis, we can't just throw in the equations for these boundary curves like we were able to do in previous examples. So we have to be a little more careful about how we're measuring the inside and outside radius to make sure that we're measuring the distance from the edge to the axis of rotation, because the axis of rotation is not x equals 0, it's x equals 3. So that's why we end up with this difference in here instead of just y. So have to be a little bit careful there. But, as long as you're keeping in mind the geometric formula or the geometric version of this formula for washers, where you have the area of the big circle minus the area of the small circle, and as long as you keep in mind how those radii appear on the graph, you won't get confused. All right, so let's evaluate this integral. We can start by moving the pi outside. Integral from 0 to 2. While we're at it, we might as well multiply out and simplify the polynomial portion here. So this is going to be 3 squared is 9 minus 6y minus y squared minus another 1. So that's going to be 8 minus 6y minus y squared dy. So pi times, and now we can do an antiderivative. 8y minus 3y squared minus 1/3 y cubed, and we're going to go from 0 to 2. So pi times, and then plug in 2. 8 times 2 is 16, minus 3 times 2 squared, so 3 times 4 is 12, minus 1/3 2 cubed, that's 8/3. Minus, and then when we plug in 0 into this, we get 0. So, let's see, 16 minus 12 is 4, minus 8/3, and 4 is 12/3. So 12/3 minus 8/3 is 4/3. So the volume of that cone with a hole down the middle is 4 pi over 3 cubic units.